Good day everyone, I am Irma Jane Pagaura. In this video, I will be proving three topics. First, function. Second is function composition. Third and last is the equivalence relations. So, let us start.
So now, I will be proving that a function is surjective. So we have a set of f from the set of real numbers into the set of real numbers defined by f of x equals mx plus b. We're told m is not 0. And we have to prove that this function is a surjective. So first, recall what it means for a function to be surjective. So f from capital X to capital Y. And here, capital X has a name called domain and Y is the codomain. And this is surjective if for every value and codomain for every little y, we can find some little x and capital X that f takes little x and sends it to y. So let's now prove this. So we have to start by taking any value here in the set. So take any capital Y in our set of real numbers. And now, we have to show that we can find an x value such that f of x is equal to y. So let's go to the side and figure it out. What is x value is. So we want f of x to be equal to y. So we want mx plus b to be equal to y. We can solve this for x by subtracting b and mx to be equal to y minus b. Then we just divide by m, and we can do that because m is not 0. That is the whole reason for having m not equal to 0. And that's going to be the value of our capital X. So now, we'll go back to the proof. We'll have to show that there exists the number x and capital X. So we have to mention this is a real number. Well, y is a real number. B is also a real number. So when we subtract, we'll get a real number. When we divide a non-zero number, it's still a real number. So this fraction is indeed a real number. And so this part's done. Now we have to write down f of x and replace x with what it actually is. So y minus b over m. And now we're gonna look for our function. So mx plus b and m and our x. So y minus b over m, and we still have the plus b. Then m is cancelled, so we get y minus b plus b is going away, so we get y. So we started with a y in the codomain. We showed that there exists x in the domain such that f of x is equal to y. So this shows that the f is surjective. So we prove that a function is a surjective.
Second is the function composition. So we have three functions, f from a to b, g from b to c, and h from c into d. And we have to prove that HOGOF is the same thing as HOGOF. In other words, we have to prove that function composition is associative. Okay, so that's the idea we want to prove. That is associative. So just to make it clear, let's pretend. I wish I could use different letters because I've already used the main ones here. But if you have GOF of x, I guess I'll use the same variables so that you can see it in relation to the problem this is defined to be. G of f of x. Okay, so it's G of fx. So that's how you compute a function composition. And this is very, very important because we're going to use this as our proof. And so we just have to show that we get the same thing. So for every, let's say, x, so for every x let's first look at this one here. So this would be HOGOF, and we're going to evaluate this function at x. Okay, so the notation here is you should very careful with the notation here. So it's h of g o f of x. So according to this definition, we have over here g of f of x is g, and then of fx, basically it works right to left. So that's how it works. So you're computing g of f of x. So here, this is going to be h of g of f of x, right? So just like our definition, our g is hog, right? So it's hog of f of x. Just like here, g of f of x. Alright, so then this again by definition is h of f, and then it's g of f of x. So okay, now let's go the other way. Let's compute the other side rather. So we have h o g o f, and again this is for x, so the notation is really key. If you're just watching this for fun, that's fine, but if you're going this for like a class or something, be really careful with your parentheses and stuff. So now this is h o g o f of x. So this is h of g o f of x, right? So just by definition, let's go back to this one. G o f of x is g of f of x. So here, h o g o f of x is h of g o f of x. So this is equal to, and so now we apply the definition here on the inside. So this is h of the HOF, and then g of f of x. We know that g of f of x. So since this is true for every x, we've shown that the two functions are indeed the same. So let me just go ahead and write that for just for like super clarity, since this holds for all x, and we have shown that what we were trying to prove, that the function HOGOF is the same thing as HOGOF. These are actually the same. So these are actually the same function composition. So it's associative. So kind of fun. Later, and if you just look at it and you don't think about it, it's really hard. So hopefully that helped even just a little bit. Lastly, for the equivalence relations, we're going to do a proof. So define a relation R on the set of integers by x is related to y if x plus 3y is even. And we're going to prove that R is an equivalence relation. So first, let me just refresh your memory. So on some of the terminology that used in this problem. So what does it mean for an integer to be even? We need that for our proof. So recall that x is even. This is by definition means that x is a multiple of 2. So x is equal to, say, 2k for some integer k. Now I need to discuss what it means for R to be an equivalence relation. So R is an equivalence relation. So R is an equivalence relation means three things. It means 1, R is reflexive. So reflexive basically means that A is related to for all A and Z, and that's going to be called reflexive. Number 2, the next one is symmetry. In basic symmetry, it basically says if A is related to B, then B is related to A, and this has to hold for all A, B, and Z. So this is called symmetry. For the third one, it is called transitivity. It says if A is related to B and B is related to C, then these two conditions together imply that A is related to C, and this has to hold for all A, B, C, and Z. This one is called transitivity. So you have a relation that exhibits all three of these properties, so we call it an equivalence relation. And they are extremely important in mathematics because whenever you have an equivalence relation on a set, you can break up the set into equivalence classes, and you have like this beautiful disjoint union of equivalence classes, and you can use it in all areas of math. It comes up in number theory, group theory, topology, and etc. So it's one of those really core foundational things that shows up in all of math. So to do the proof, I could have just jumped into it, but I thought I would spend a little bit of time talking about what's going on. So just to give you some extra knowledge, so let's go ahead and prove reflexivity. So first, I'll just say reflexivity. So for reflexivity, we have to show that A is related to A for all A and Z. So here, this is what we're going to be using the whole proof. Okay, so to make sure you can see it, so we have to show A is related to A. That basically means that A plus 3A is even. So take any in the set of integers, then let's look at the quantity A plus 3A. Well, that's simply 4A, which is 2 times 2A, where 2A is an integer because it's the product of integers. So A plus 3A is a multiple of 2, right? So that's our K in the definition. So you see how it says X equals 2K. So that's your K. So that's your K. So that basically means that A plus 3A is even. So A plus 3A is even, hence A is related to A and it holds for all A. So it's reflexive and we're done with that part. Now let's do symmetry. For symmetry, we assume that A is related to B and we have to show B is related to A. So suppose that A is related to B, so that means that A plus 3B is even. So that means that A plus 3B is a multiple of 2. So it's equal to 2 times some integer, which I'll call K for some integer. For some integer K, very nice. So now we have to show that B is related to A. That would mean that B plus 3A is even. So the natural thing to do is to look at B plus 3A. So then B plus 3A, well, let's see if we can figure this out. So if we solve this for a long time, so A is going to be 2K minus 3B. So it will be plus 3A, solving for A is 2K minus 3B. So this is 2K minus 3B. Right, so just subtract 3B from both sides. So that is B plus 6K minus 9B, which is negative 8B plus 6K, which is equal to, now you can pull out a 2 here. This will be negative 4B plus 3K. So did it correctly, right? 2 times negative 4 is negative 8B. So where negative 4B plus 3K is an integer because it's a product and sum of integers. So it's an integer, so this means that B plus 3A is even. Hence, B is related to A. So we started with the assumption that A was related to B and we showed that B was related to A. So that shows that it's symmetric. And the last one in transitivity. So transitivity, and I'm going to go ahead and write the relation down again over here. So just because you can see it anymore. So it's up here, right? So I'm just going to write it somewhere convenient. Maybe I'll write it here. So you write it here, so you see it. So X related to Y. If X plus 3Y is even, that's our relation. That's the one we're using in this proof. So for transitivity, we assume that A is related to B and B is related to C. And then we have to show that A is related to C. So we say, suppose A is related to B and B is related to C, then that means that A plus 3B is even and B plus 3C is even. So that means that A plus 3B is equal to 2K and B plus 3C is equal to 2P. So for some integers K and P, so for some integers K and P, we need to show that A is related to C. So right, we need to show that A plus 3C is even. Okay, that's the goal. A plus 3C. So typically when you have something like this, you can add them and stuff usually happens add or subtract. So let's just try it. See if we can figure it out. I have done this yet. So then a plus 3b plus b plus 3c. It is going to be, what is that going to be? Well, it's going to be 2k plus 2p. As we can combine this, a plus 4b plus 3c is equal to work k plus 2p. We're looking for a plus 3c, right? Because that's a related to c. So now, maybe what we can do is we can subtract the 4b. So a plus 3c is equal to 2k plus 2p minus 4b, right? So subtract it over. Now you can pull out a 2k plus p minus 2b. Right, so 2k, 2p minus 4b, where k plus p minus 2b is an integer. So a plus 3c is even, so a is related to c. So we started with related to b and b related to c, and we showed that a was related to c. That shows transitivity. So therefore, we've shown that it is reflexive, symmetric, and transitive. Therefore, it's an equivalence relation. So thus R is reflexive, symmetric, and transitive. Hence, it is an equivalence relations. And that completes the proof. So that's how you show our relation is an equivalence relation. So that would be all. Thank you, and may God bless us all.